everybody. This is joint work with Dennis Murphy and Jen Gunn, both of whom used to be at University of Buffalo, but Jen graduated now. He is working at Meta. So as part of this talk, I'm going to be talking about secure multi-party computation in general, and this is a way to actually transition from passive or pseudonymous security to a malicious security, and we're going to primarily be in the setting where we use secret sharing. And so just to get you in the framework, right? So the solution that we're developing applies to any type of computation that somebody might be desired to do. So we're just thinking about there are certain participants that have private inputs. They enter their inputs in a computation, and in this case I'm saying using secret shared form. There are some participants who are going to be running the computation, and then the results get delivered to one or more parties who are going to assemble the results. So for the purposes of this part, the exact computation is not necessarily important. We're looking at the general formulation of this problem. And so when I started looking at this, we're primarily looking in the setting with the honest majority, which means that there's the total of n participants who are running the computation, so that there are computational parties, and we require that less than half of them are corrupt, right? So the majority of the participants have to be honest and not colluding with each other. And so this is something, or this sort of compilation from passive to active security is something that's been around for some time, and started in a way with the sort of the concept that we're using was started with speeds, and there's other work that follow, but in the context of honest majority setting. So what we have is that we start with the building blocks that were shown to be secure after additive attacks. We're looking at elementary operations such as additions and multiplications in arithmetic circuits, where the only error that an adversary can introduce is an additive error. So this is something that's been shown before, for the protocols that we typically consider. And the way this proceeds is that we run computation on shares the way we would. So this square bracket notation means that the values are secret shared, they're protected. For inputs, the intermediate results, everything. So we execute one thread the way we would, and then we execute another branch where everything is randomized by a global private value, random value. The idea is that you evaluate two of these branches, and before you can disclose any results, you will make sure that they're consistent between each other, right? So the purpose, the purpose of this random number is to ensure that if the adversary tempers one of the branches, that it won't be able to tamper with them consistently, because of the secret is something that they don't possess. That's the idea, right? So this is where we started. And when we started looking at this, the issue that we came across is that the idea or the security analysis in this dual execution framework was presented in the case where we have arithmetic circuits that have only two gates, addition and multiplication. But when we start using them in practice, the efficient protocols that were developed have actually more elementary operations than only these two operations. And I would like to look at as a simple example of comparison that is somewhat difficult to do in the setting, right? It's ubiquitous, but we'll need to be able to realize it in this setting. And so what we have in this case is that I'm using the example of a comparison, so less than. And typically the way it's realized, if you have two arguments A and B that you'd like to compare, you compute the difference and you compare the difference to 0, right? You want to know if the most significant bit is positive or if it's 0 or 1. And so typically the way it proceeds is that we produce a number of random bits, we create this random mask, we add it to the private input that we have, we open that protected value, at which point we have access to the individual bits, and we continue computing on the individual bits, which is going to be faster because the comparison operation actually, what we need is we need to look at the most significant bit, right? We need to determine the most significant bit for this operation. And so The issue in this case is that somebody analyzed an arithmetic circuit, but what we actually use is not a pure arithmetic circuit. And so where we, sort of started this work, we said, okay, we need to determine the set of gates, elementary gates that people might use in an operation. And for the purpose of this talk, we're focusing on field-based computation, something like Shamir security sharing. And so in this case, if you look at these two in the middle, there are addition and multiplication, but there's also two types of randomness that can be generated. There's a random element of the field, and also a random integer of a specified bit length can be produced for statistical hiding. So the first one is going to achieve perfect hiding. This one is for statistical hiding, where you'd like to avoid wraparound. And also that there is an open gate, which is fundamental, right? It's used often. And multipop is primarily for efficiency reasons, where it can do multiplication and open at the same step, and it's going to have better performance, but fundamentally it's not changing the functionality, right? It's for performance reasons, and this is why I'm saying it's optional. All right, so where we take this is that we sort of analyze the logic of the the setting, and we show that it's not always safe to delay verification until the very end before the inputs get disclosed. And intuitively it makes sense. For example, if we look at, say, statistical hiding that uses integers of a particular side, if the adversary was able to tamper with intermediate results and, say, inflate the input, the private value that is supposed to be short, and we use statistical hiding to protect it, now it's actually not guaranteed that the value is protected, right? So we have some additional examples in the paper, but intuitively, if somebody tampers with the intermediate results, it doesn't mean that, like, when we open, we can disclose information about those values. And so where we take this is we modify the solution. We create our own compiler from passive to active security. And the way it works, there's a couple of different steps. So the first thing that we need to do, we treat this as an extended circuit that has, in addition to additional multiplication, has some other gates. And we analyze under what circumstances it's safe to call an open functionality. And intuitively, sort of, you can think of, if I'm only generating randomness, say I want to generate random bit and I'm opening, it's not possible to reveal anything about private inputs. In this case, so it would be safe to proceed. But in some other cases, it's actually not safe. And we present an algorithm where we analyze the computation and say, you have to inject verification at these points in the circuit. And then what we need in addition to that is we also need to demonstrate that our construction in the semiotics model with passive security is secure up to additive attack, because this logic assumes that you have to have security up to additive attacks. And this is somewhat complicated. It also has a couple of different steps. We need to re-examine the notion of linear protocols, which were addition and multiplication before. We show that others are also linear, except that open. We couldn't show that open is secure up to additive attacks, so we sort of treat it separately. And then we formulate the notion of extended linear-based protocol that combines all of the different gates that we have. We'll look at specific instantiations of the gates that we have. We prove them up to secure up to additive attacks, and now we have the starting point where this extended circuit is secure up to additive attack. And at this point, we're ready to proceed with a compiler that uses this notion of dual execution, where we run one branch and we run a randomized branch. And we also basically inject verification at the places where our algorithm said you have to verify prior to opening. Open is a special case. We basically need to use the version that is secure up to malicious attacks. because it cannot be um, secure in the setting where we require that it's secure up to additive attacks. And so in this context, we obtain this compiler that starts with a version that is secure up to additive attacks. We use open gates that are secure against malicious behavior, and we sort of check in more places than just MDM. All right, so what I wanted to show at the end, so obviously the details are in the paper, there's proofs, it's a little bit tedious to show different properties, but what I wanted to demonstrate that we haven't seen in previous works that are similar is the gap between passive and active security. So on this slide, what we have is how many operations are run in a batch at the same time, and we'll look at different operations. These are addition multiplication comparisons, less than equality, and this is over the threshold Euclidean distance, which is basically that product followed by a comparison. And so in this case, this is the size of the vectors. We might want to look at, say, 1,000 of them executed at the same time, because if you execute only once, then the latency is significantly impacting performance. But if you see, look and say this column, is that active security is about 2 to maybe 3 times slower than what we have in the presence of just passive security. So the gap between these two is actually pretty small these days. All right, so I think I'm out of time. I would like to conclude and say that this work's been in the context of field-based computation, such as Shamir supercherry. But because there's been like a lot of push to operate over a ring, which is sort of native to the CPU instructions that we're using, that could be significantly faster. And as a part of ongoing work, we're also looking to modify that to the ring setting, to the decay, where we need to slightly change the gates that we consider, but overall transition is going to be similar. All right, thank you.
Well, thank you very much. Do we have a quick question from anyone?
Thank you for the talk. What happens in case the entire circuit that we are doing calculating is deterministic but not random? Do we need to inject verification steps in between them?
If you're not using open, right, so everything is deterministic, then you wouldn't be able to protect with randomness in open. Open, fundamentally open is the problem, right? If you're not calling open, then you can proceed until the end.
Okay, thank you.
Do you want to go really quickly?
I just want to make sure the dual execution is still as before. The difference is the stronger analysis that proves it actually works with the new gates.
Yeah, so you can use dual execution, right? We're just saying that you need to be checking more often than just once at the end.
Okay, let's thank the speaker again.